All right, this is lesson 6.1, so chapter 6, section 1, and it's the inverse trig functions, which I think you're going to enjoy. It's going to go, I think, fairly smoothly. We've done inverse trig functions before, not quite the depth that we're going to do them now in chapter 6, but it's something you're familiar with. Okay, so inverse trig functions, first of all, notation. Two kinds of notation. Sometimes I'll put the little -1 up here, which means inverse, or older notation, I'll call it arc. Sine, arc, cosine, arc, tangent, both mean the same thing. Both mean we're using the inverse trig function. All right, one point of confusion that some people have, inverse is a different idea than a reciprocal. So some people see sine inverse and they think, oh, that must be the cosecant. It is not. Cosecant is a reciprocal, so the cosecant is 1 over sine. But the sine inverse is not related to reciprocals. So that's very, very important to understand. And you see people confuse that once in a while. So they'll see the inverse and think of it as a reciprocal, and they are not. Which is sometimes why that second notation is better. There's no doubt, arc cosine, that's no confusion with reciprocals. Whereas that -1, you can kind of see why people might confuse that with a reciprocal. Okay, so we know what is not an inverse trig function. Let's see what it is. And let's start just with a regular sine function, not an inverse function, just a regular sine function. I'll put in an angle, such as pi 6, and I take the sine of pi 6, and it gives me out an answer 1/2. So I start with an angle, can be measured in degrees, can be measured in radians, I end up with a number between -1 and 1. All right, what does the inverse trig function do? It works backwards. You basically flip your x and your y. You switch those around. So the inverse trig function, I put in the half, and I get the pi 6 for the answer. So I put in a number between -1 and 1, and I get an answer that is an angle. This time it's measured in radians. Typically it's measured in radians. It could also be measured in degrees. And if you think about solving triangles, we've done that. When we're finding the angle in a triangle, we would be in degrees. We'll take the sine inverse of something or the cosine inverse of something, and we will get our answer in degrees. We'll get an angle in degrees. Okay, so it's worth practicing a few of these, and before we practice, I want to find a little white space here. I guess I'll have to opt for the side here, because it is always helpful to remember your chart. And let me just, I think I can fit it down here. Let's sketch your chart. Remember from the beginning of the year, with a sine and a cosine and a tangent in it, we'll call it S and C and T. And then we had 5 different values that you had to memorize. Ooh, kind of narrow here. Hopefully you can fit it in there. And it was for 0, 30, 45, 60, and 90 degrees. Sine, do you guys remember, was an increasing function. It was 1/2, root 2 over 2, root 3 over 2, and 1. Cosine was the exact same thing in reverse. And I remember very early on telling you guys, why don't you just memorize this? It makes life a whole lot easier. I think a lot of you guys did. And it does make life easier. So we had these values for tangent. Tangent, remember, was sine divided by cosine. This turns out to be root 3 over 3. And this one is just root 3. Okay, so we need this chart. We'll refer to this chart. And now we do some of these. What's the sine inverse of root 3 over 2? Well, here's root 3 over 2. Oh, one more thing I should do. I made the chart in degrees. We also might remember radians. So 0 degrees is 0 radians. 30 degrees, if you remember, is pi 6th. 45 is pi 4ths. 60 is pi 3rds. And 90 is pi 1/2. And I haven't looked in the book. Let's just stick with the radian measures. Neither one is all that hard to give. So the sine inverse of square root of 3 over 2, there it is. I can give 60 degrees, or I can say pi 3rds. So why don't we just give both? Sine inverse of 0, where's the sine 0? 0 degrees, or 0 radians. Where's the sine? Pi 1/2. Don't get fooled. They may think it was 1. It is not 1. Sine inverse, I want to start with a number between -1 and 1. Pi 1/2, pi is like 3, a little more than 3. 3 point whatever. No way is that less than 1. So what's the sine inverse of pi halves? We can't do that. That's not defined. We wanted an angle for the answer. We didn't want to put an angle in an inverse trig function. What's the sine inverse of 1? 90 degrees. Or pi halves. We can do the cosines as well, or the tangents. Let's skip down to number 9 because we've got the cosecant inverse of 2. And so the cosecant is not on our chart, so we take the reciprocal. The reciprocal of cosecant is sine, so we have the sine inverse. We also then take the reciprocal of the inside. So the cosecant inverse of 2 is the same as the sine inverse of a half. Where's the sine of half? At pi 6, or 30 degrees. One of those two. All right, do these other two. Secant inverse is like a cosine inverse, the reciprocal. So I've got the cosine inverse. I take the reciprocal. I rationalize it. And I'm going to get the cosine inverse. I get 3 root 3. And the bottom I get 2 times 3. Oh, look at that. 3's cancel out. So I've got the cosine inverse of the square root of 3 over 2. That's on my chart. That's 30 degrees. Or pi 6. Similarly, for the cotangent inverse of root 3 over 2, we do the tangent inverse and we would rationalize it. Okay, so for positive numbers, this is not a bad thing. We would like to expand this and put negative values into these inverse functions as well. But that's going to take a little more work. So right now everything was either 0 or positive. Let's think about what happens when we put negatives in these inverse trig functions. Okay, a few facts. First of all, we want these to be functions, so we want these to pass the vertical line test, meaning if I put any value in there into my inverse trig function, I should get one answer. So when I came back here and I said, look, the sine inverse of square root of 3 over 2 is 60, or pi 6 in this very first question, you might have also thought, what about 120 degrees? Because isn't the sine also positive in 120 degrees? Haven't we just finished doing the law of sines? When you take the sine inverse, you can get 2 answers. And so to make these functions, we have to stick with one answer. And so what happened is, when possible, we stick with the first quadrant answer. Okay, so let's come back here and look at this again. So see if we make sense out of this. When I'm taking to have a function, I better get a unique value. And to do that, we have to be very careful about which value we give, because sines, cosines, our trig functions are repeating functions. They take on the same value many times. Okay, so 2 facts we need to make this all work out. First fact is, if it's anything positive, if you take the inverse of anything positive, give the first quadrant answer. A smart trig class. Everything is positive in the first quadrant. Don't worry about it. Give that answer. Don't give some other answer, because you want it to be a function. Give the first quadrant answer. All right, fact 2. When we're taking the inverse of a negative, we do not have one quadrant where all the trig functions are negative. So when we're looking for negatives, unlike the positives, where they're all positive in the first quadrant, we can't find just one quadrant where all the trig functions are negative. So we have to kind of move around a little bit. So cosine, secant inverses, we'll use the second quadrant. Sine, cosecant, we'll use the fourth quadrant. And then tangent and cotangent, they kind of split up. Tangent, you give the fourth quadrant answer, and cotangent, you give the second quadrant answer. And these are just conventions that we will have to remember. Because again, these trig functions repeat, they take on the same value multiple times, but to make it a function, we all have to get the same answer when we take an inverse. And so the conventions are these. First, when it's positive, go with the first quadrant, no big deal. When they're negative, it depends. Sometimes the second quadrant we'll look in, sometimes the fourth quadrant. Never will we look in the third quadrant. It'll always be adjacent to the first quadrant. First and second, or first and fourth. Okay, let's try this a little bit. let's take the cosecant inverse of negative 1/2. So now we've got a negative. We can look at our chart and say, oh, I'm looking in the second quadrant. Maybe you go through reference angles. What's the cosine inverse of positive 1/2? That would have been 60 degrees is your reference angle. So now think about that in the second quadrant. Back up 60 degrees. If I back up 60 degrees, it looks like 120 degrees, or in radians, 2 pi thirds radians. So just be careful with that. Cosine inverse of a negative, we better look in the second quadrant. Sine inverse of a negative, we better look in the fourth quadrant. And there's another convention that makes these really easy. Okay, let's just start with a half. What's the sine inverse of a half? Where's the sine of half? 30 degrees, or pi 6. So now we come down, to the fourth quadrant. We back up 30 degrees, or pi 6. And again, you might be thinking, oh man, reference angles, what's 360 minus 30? And it turns out we make this a little bit easier. Since we backed up 30 degrees, or we backed up pi 6, we just give the answer as negative 30 degrees, or negative pi 6. And that's the same thing as saying 330 degrees, but it's easier to say, oh, back up 30 degrees, or back up pi 6. Same thing for the tangent inverse. Look in the fourth quadrant. I know my reference angle is 45, so negative 45 degrees, or negative pi fourths. And how about the cosecant inverse? We don't have that in our chart. So the sine inverse. Negative 1 over root 2, we'll rationalize that. And it's a sine inverse of negative square root of 2 over 2. Reference angle is 45 degrees. So negative 45 degrees, or negative pi fourths. And that takes care of the inverse trig functions. All right, one last problem I'd like to show you that's a little more involved. A little bit of trickery in this, but I think you're going to like this. And we'll practice this more in class on Monday, too. Okay, let's look at a combination function here. It is the sine of the arc cosine, and arc cosine is the same thing as cosine inverse. So the sine of the cosine inverse of 1/4 looks like a mess. Let's start on the inside, the arc cosine of 1/4. What does that equal? Especially without a calculator. Without a calculator, what does that equal? The arc cosine of 1/4, what does that equal? I don't know. But I know inverse trig functions give me angles for an answer. So whatever it is, I'm just going to call it theta. So what happens over here is I've changed the question. It's still the sine, and I know this arc cosine is going to give me an angle for an answer, and I'm calling that angle theta. So this is really equivalent to the sine of theta, this question. So I kind of changed the question around a little bit. Say arc cosine of 1/4, I don't know, but it's some angle. So it's the sine of theta. Okay, then I come back over here to the right side and try to figure out what I just did. I still got to figure this out. And the trick is, since it's arc cosine, let's take the cosine. Not of one side, because you know algebra. Take the cosine of both sides. On the right side, I've got the cosine of theta. The left side, I've got the cosine of the arc cosine, or the cosine of the cosine inverse. Inverse functions always cancel out, so they cancel out, and I'm left with 1/4. So the cosine of theta equals 1/4. So I go way back now in my trig. I draw a right triangle. And I'll label this angle here theta. And you guys remember SOHCAHTOA, cosine is adjacent over hypotenuse. So I can label my sides. Here's the adjacent. Here's the hypotenuse. I could use Pythagorean theorem and go 4 squared minus 1 squared is 15. I've got the other side is square root of 15. I'm ready to go. Let's get the sine of theta. SOHCAHTOA, sine is opposite over hypotenuse, opposite the angle. Sure glad I figured that out. Square root of 15 all over the hypotenuse, which is 4. So the sine of theta is a square root of 15 over 4. There's another one of these on the note sheet, but I think we've done enough for right now. Some people, one example will be enough. You'll have it. Other people will need to practice this more on Monday, and that is A-OK. So thank you guys for watching this. Hopefully you've had a nice weekend. And this is my shout out to JoJo. But you only get to hear it, JoJo, if you watch the whole video. So on Monday, when you come in, JoJo, we should have a secret handshake or something so I know that you watched this video. So we will see what happens when you come in on Monday. Preferably on time, JoJo. All right. Thanks for watching, guys. Have a good weekend.